Okay, let's move on to the next speaker, who is, okay, I want to get my program and make sure I have the title right. It is Soudip Mukherjee, who is going to talk about a panorama of the universe with multi-messenger observations. Soudip is from Perimeter Institute. Okay, it's there on his slide. Thank you. Please go ahead, Soudip. If you are speaking, we are not able to hear you.
Right. Sorry about that. Yeah. Thanks, everyone. Thank you, Satya. So thanks first of all for staying this long late in the evening for the talks. And thanks for the organizers for inviting me to talk on multi-messenger cosmology today. So as the title says, I'll try to cover a couple of topics on what we can do in the field of, particularly in the field of cosmology, by combining observations from both gravitational wave sector and electromagnetic sector. So, and why is this particular topic quite interesting? And is because we usually have learned from that we learn more when we combine data sets. We learn more when we measure something differently, and we do this in our daily life. So why don't we do that to study cosmology? Can we study cosmological aspects by combining multi-messenger observations, such as gravitational waves and electromagnetic observations? So I'm not going to talk about neutrino sector today, of course, but there's also another sector which is equally playing a role in the future. So in the electromagnetic sector, we are blessed to have detectors across multiple bands, starting from all the way to radio, just now heard from Pratik on the topics, to way up to extremely high frequency signals come from gamma rays. And we have pretty much ability to map the sky across all these bands, nearly full sky maps. Similarly, the story is going to be for gravitational wave sector, where gravitational wave emissions you expect from a wide range of frequencies, starting from extremely low 10 to minus 17 hertz or so, which is possible to be detected from cosmic microwave background, B-mode polarization. You have nanohertz signal, which you expect to detect from pulsar timing array. Then at millihertz, you can have signal from from LISA. And in the extremely high frequency range, you can detect signal from LIGO Virgo Kagura, which is currently operational, and in future from Cosmic Explorer and Einstein Telescope. And this whole topic is extremely interesting because you have now started observing the cosmos with a completely new kind of species, like black holes, neutron star black hole systems. So here I'm showing you kind of a summary plot to show what is the redshift range and masses of the kind of sources with which we are going to explore the universe in the coming decades. So in the left-hand side, you are seeing the plot from possible from ground-based gravitational detectors, extremely high frequency one. And you can see in the x-axis the mass distributions of the gravitational sources, and in the y-axis is the redshifts. So what you can realize is that with LIGO, advanced LIGO, we can reach almost a redshift of 1 in this mass range about a few tens to 100 solar mass. But with third generation gravitational detectors such as Cosmic Explorer and Einstein Telescope, our reach will be basically almost beyond a redshift of 50. Similarly, for sources detectable from LISA, they are heavier. They are about a few million solar masses. Again, detectable something up to a redshift of 20 or so from LISA, which is possible to in the next decade. And if you combine both these sectors, the electromagnetic probes and the gravitational wave probes, the question now comes, what exciting and new topics can we learn in the field of cosmology and fundamental physics? There's certainly several topics one can learn also from in the astrophysics sector. But unfortunately, I'll not be able to cover it today, but that doesn't mean that there's not interesting topics over there. So to give you a very summary, one side of what we are today in the field of cosmology is that we have made several interesting measurements with the help of cosmic microwave background, large-scale structure, supernova, and so on. And our measurements have showed us that we are typically in a state where we are in an accelerating universe with 68% of it, we do not know what it causes. We call it dark energy. About 26% of the matter density also I do not know, which is called dark matter. And about 5% is ordinary matter, which you can possibly explain from our terrestrial physics we know about. So with this standard picture which we have right now, the question is, what can we get new or in the field of gravity using multi-messenger observations? I have listed here a few questions which are pretty interesting for a cosmologist, and these are not just only questions. There are several more, but a few of the important questions right now are like, what is the current expansion rate of the universe? We call it the Hubble constant. What is cold dark matter? What is dark energy? Is it really the cosmological constant? And is general theory of relativity, a basic paradigm under which we work in the field of cosmology, is that the correct theory of gravity? And the place where multi-messenger will play a big role is basically in combining two sectors. In one side, you can ask how from the transient sources, which are detectable way up to the shift of 50 or so in the future, what can you learn about the cosmos, the physical cosmology? That's the first part. Another part is from our existing observations in the EM sector. So whatever observations we have made up to high redshift, what can you learn about the properties of the binary systems through these observations? So basic point is, can I understand about this mass distribution of black holes? Can I understand about these merger rates? And can I then talk about several formation channels of the compact objects? In my today's talk, I will again not be able to cover the topic which is related to this part, which deals about what we can learn about astrophysical properties of the binary systems. But rather, I will focus on the first part, which talks about the physical cosmology and what we can learn from gravitational wave sector. So let's focus at first on what can we learn from about the expansion history from these binary systems. So we have specifically two kinds of sources. We can classify the sources for which we can detect electromagnetic counterpart. We call them the bright sirens. And sources without electromagnetic counterpart, we tend to call them dark sirens. And one of the interesting answer which we from the gravitational wave field would like to address in the coming years is that what is the value of the Hubble constant? Though it is almost like 100 years since Hubble discovered Hubble constant, measured for the first time, it still is not resolved that what is its true value. The highest value of Hubble constant is something, shows you something around 67, whereas the value of Hubble constant from the low redshift probes shows you something above 70, something around 73, 74. And when you combine this, all the low redshift probes of the Hubble constant, you tend to see there is a 4 to 6 sigma deviation in the value of Hubble constant from the early universe probes, such as cosmic microwave background or BA. This tension is not solved even after several years of attempts in both theory or systematics. So we really do not know what causes this. And why gravitational wave is going to play a big role here, I'm going to tell you for both the bright sirens and for dark sirens. So let's at first focus on bright sirens part. So this was first time proposed by Bernard Schutz back in 1986 that gravitational wave sources are an excellent distance tracers, and one can use that to measure Hubble constant. And this idea was applied by the LIGO collaboration in 2017, when you have first seen a bright standard siren called GW170817, for which we measured the luminosity distance. There's a massive effort to see its electromagnetic counterpart and identify the galaxies. We indeed made that too. And when you combine both of them, and you correct for the peculiar velocity shown by that VP over there, the ratio of these two quantities gives you a handle on the Hubble constant. And that's below is the curve for the first measurement of Hubble constant from a bright standard siren made by LVK. After this,
did we lose Sodeep or?
No.
I think he's having some challenge with this changing the slide.
Yeah.
Able to hear us, Sudeep?
Yeah, I can hear you. Can you hear me?
Yes, we can hear you.
But my slides were frozen for some reason.
Share it, redo it.
You can escape from the.
Yeah, can you just kick me
Sure,
out?
no problem. Not a problem.
You want me to stop?
Sharing, yeah, then I can restart the sharing again.
Oops. Yeah, we have. Hopefully, that should have thrown your sharing.
Yes,
okay,
perfect. And I'm really sorry for this glitch. I don't know what exactly happened.
Well, it's not your fault.
I hope now it's changing, right?
Yes,
yes.
Good. So as I was saying, we have made this measurement from the Lycopodium collaboration. And then there are several works, I've listed only a few of them here, which have shown how for bright standard sizes, such as binary neutron stars, one can make a measurement of Hubble constant in future. Here you are seeing a plot from Chen et al. 2017, where they have shown that with about 50 binary neutron star events, we can get to a measurement of Hubble constant something like around 2%. The year time scale over here, 2023, maybe looks a bit optimistic right now, but of course, this is a very promising channel. With more events, we are going to get there. Right now, we have one event for which we have detected electromagnetic counterpart. What about the other sources, like the sources which do not have electromagnetic counterpart? So those are like binary black holes or any binary neutron stars for which you do not see electromagnetic counterparts. The advantage of these sources are that they can be detected up to high redshift because they are more luminous if they are black holes. And if we go up to high redshift, we can possibly see cosmological expansion history beyond this impact from Hubble constant. So we can start seeing the impact from dark energy. And possibly we can now get into at the part where we can go to cosmological parameters beyond Hubble constant using dark standard size. So let's be talking about now black holes. If we do not detect their electromagnetic counterpart, but I measured their luminosity distance pretty well, how am I going to map its expansion history? Because what we have learned from Cosmology 101 back in grad school is that we need both luminosity distance and redshift to measure the expansion history and the cosmological parameters. So let's ask these questions. How these black holes are going to be distributed spatially in the sky? Are they going to be distributed randomly, or are they going to be distributed non-linear random fashion? So let's take this simple image over here where I have put some yellow stars. They are the dark sirens for me. I have measured the luminosity distance. So are they going to be really homogeneous, distributed? The answer is no, because you are not going to be random positions, but rather they're going to be in a position where you are going to see the galaxies. So here you are seeing an image where the dark regions are the places where you have galaxies, and the white regions are the places where you have no galaxies, or called the voids. So you expect to see galaxies at the main places where stars form. From stars, you form the black holes, and they are the hosts of the black holes. Now, the point is that for these sources, one of the extremely important aspects of galaxies is that it's spatially clustered. Galaxies shows this property. We have measured it from several years of observations. And also for these sources, we can measure the redshift. So now we have two friends. One sector measures luminosity distance very well, and the other sector is the galaxies, which can measure redshifts very well. But the key question now is how you connect these two sectors, how gravitational sources connect with the dark matter distribution. And that's a quantity which is of fundamental interesting to us, but we do not know. It's called the gravitational wave bias parameter and its redshift dependence. So let's focus on a single object for timing. So the main point is that when you see a gravitational wave source, even though it has a very poor sky localization error, if it is hopefully not extremely bad, not like something like 100 square degrees or so on, but if it is something like 10 or 25 square degrees, you can start exploring the spatial clustering between gravitational wave sources and galaxies. And we have shown in these papers that this is one of the key ways to infer the clustering redshift of gravitational wave sources from LIGO, Virgo, Kagra detectors. And this makes it promising to basically measure the redshift to the dark standard sirens. So the way this method works in a simple way, if you, in one sector you have gravitational wave sources, let's say for which you have measured luminosity distance shown in the left-hand side, and the same part of the sky you have measured galaxies. For this example, say spectroscopic galaxy surveys. So what you are now asking is the spatial correlation, which is called as a cross correlation between the gravitational wave sources and galaxies, to infer the clustering redshift. So let's do this exercise quickly. You are calculating this dp quantity called the probability, the excess probability of finding clustering in comparison to a random distribution as a function of redshift. So when you correlate with a particular tomography of redshift, you basically see no correlation. The dp value is close to 0. You go to the next one, you again see something close to 0. Go to the next one now, you now see slightly more correlation that this particular redshift bin with the gravitational wave sources. And as you proceed next, you see again as almost consistent with 0 correlation, and the next one too. This means you have now inferred this particular redshift as something as the clustering redshift of the gravitational wave sources. When you combine that with different tomographic bins of the luminosity distance and the gravitation and galaxies, you basically can start mapping the expansion history of the universe. But to do this, one of the key part is we need spectroscopic samples or photometric galaxy samples to do cross correlation. What are those? Are they full sky? So here is a plot you are seeing where I am showing you the number densities of upcoming galaxy surveys such as Sphere-X, DAISY, Euclid, and also in different colors, and also the number of gravitational sources number density for different merger rates in green, gray, and dark red. And the shaded region in the redshift space you can see is basically the region which you cannot measure gravitational wave sources with high signal to noise ratio. That means anything in the left-hand side or less than 1.2, 1.1 to 1.1 is something how you can measure. And now there is a significant synergy between Sphere-X and DAISY with the LIGO, Virgo, Kagra network of detectors. And what I have shown with my student Diaz, Christina, that by cross-correlating the LIGO, Virgo, Kagra sources in its design sensitivity with the Sphere-X sources which are detectable full sky, and DAISY, which is about 9,000 square degrees, we have taken over here, we can get to 2% or about 1 to 5%, 1.5% measurement of Hubble constant with 5 years of integrated time after marginalizing over bias parameters and its ratio dependence. And this quantity itself will start going to give you the first measurement of the bias parameter of the gravitational wave sources and also its ratio dependence. Nevertheless, this is not the only story. There is also, you can measure something called as the dark energy equation of state and its ratio dependence as W0 and WA parameters. That's more futuristic. Here is a forecast for what you can do with LIGO, Virgo, Kagra network of detectors, again using the cross correlation technique. But now with 3,500 gravitational wave sources, we can get to something like around 6 to 8% measurement of dark energy equation of state solely from GW observations. So if you combine that with EM observations, you're going to get even further. And these all measurements are going to dramatically improve as you have third generation gravitational detectors, multiple one, get a better sky localization. In the last couple of minutes, I would like to cover a topic on what can we do beyond the standard model, or to start talking about things like beyond general theory of relativity. It goes without saying that gravitational wave effects, because of its propagation through space-time, brings a completely unique way to measure GR. And one of the ways is basically to explore its propagation effect or measuring something called as the damping term or the frictional term, which is shown by this gamma Z parameter over here. Remember, from GW 170817, a bright standard sirens, we have already put constraints on the speed of the graviton in comparison to photons and the mass of the gravitons. That's the term which are shown in the red box over there. But the term in gamma Z typically have the impact on its luminosity distance, which if it is greater than 0, it tries to enhance the signal. If it is less than 0, it tries to minimize the signal. So if we can measure this quantity, it is going to be a direct probe to theories beyond GR. But the problem is that we can measure the left-hand side of the quantity pretty well from observations, but in the right-hand side, all these quantities are unknown. For a given galaxy, it is not possible to measure its luminosity distance unless we have a standard candles over there, or some standard scales such as baryonic acoustic oscillation. So what I have shown here that it is possible to do an absolutely new multi-messenger test of GR from the gravitational wave propagation when you basically combine 3 length scales in cosmology. The length scale coming from luminosity distance measurements of gravitational wave sources, that's the quantity in the left-hand side. You combine that with the baryon acoustic oscillations of the large scale structure galaxy surveys. The product of these 2 data sectors as a function of redshift should be just a 1 plus z times sound horizon, which you can again measure from cosmic microwave background data. And if GR is the correct theory of gravity, then the term which is in the box in the red will be actually consistent with 1 at all redshifts. But if there is any deviation from GR at any redshift, we will be able to pick up that by this particular tomographic study, which I'm showing you over here, which is the beauty of this aspect is that it tries to compare 3 different length scales, and it's a complete measurements driven by data. And how promising is this? Here is a plot of the relative error on the parameter called Xi naught, which basically captures the deviations from GR. Its fiducial value is 1 for GR. And we can show that this quantity we can measure again from LIGO Virgo Kagra network of detectors in synergy with something like SphereX. We can get to about, let's say, 2.5% measurement with around 2,000 objects, which is totally not bad because currently we have almost no interesting measurement on this quantity. And the deviations are expected to live something around 5% or even less. For
3 minutes over there. 3 minutes.
Sure. So with this now, I will, I'm towards the end of my talk, I'll not talk much about the other aspects, such as what you can do from stochastic gravitational wave background. I particularly told you today about what you can learn about cosmology from bright standard sirens and from dark standard sirens. But nevertheless, there are several aspects which can open up from stochastic gravitational wave background. And one of them is the field of cosmology, which is very interesting, is about primordial black holes. We can compare the merger rates we can infer from star properties of stars, as shown in the left-hand side plot. With the merger rates we expect, even if there is a delay time for different formation channels of black holes, and that's the plot you are seeing the right-hand side. What is the key is that if there are primordial black holes, one of the smoking gun signature is that the merger rate at high redshift is going to be several orders of magnitude higher than what you would have expected from just stellar black holes. That's a smoking gun signature. And what we have shown is that this one can probe by simply the stochastic gravitational wave background because it basically measures anything which is there at high redshift. So if I have more black holes, I see more louder background if I have less black holes. And this particular approach makes it possible to distinguish astrophysical black holes and primordial black holes combining with these EM observations by basically seeing the shape of the stochastic gravitational wave background spectrum, as I've shown over here. I will not go into much over the details now. I would rather show you one of the simple plot over here is about the forecast, which you have obtained for O5 and A+. And it is very promising to tell that if primordial black holes exist in the mass range around 30 solar masses, stochastic gravitational wave background will be able to give us a hint on that directly with O5 and A+. And this will be one of the, like a pathfinder for third generation gravitational wave detectors to tell them what are we going to see already at high redshift. With these, I'm towards the end of my talk. I have gone very fast to a couple of topics which you can explore through multi-messenger cosmology using both resolved events such as Hubble, such as binary neutron stars, neutron star black holes, and binary black hole systems. Also from stochastic gravitational wave background, you can do a several amount of works and mainly from inferring the merger rates. And these are all possible because of the efforts from several people who are working on these collaborations and measuring the data. Right now, the HLV is operational. HLVK will be operational from O4. Hopefully, LIGO India will be joining us from the end of this decade. LISA is already funded and is going to be operational likely from 2035 onwards. And currently, the third generation detectors we are under it is already proposed, and hopefully will be operational from 2040 onwards. And this is indeed a right time to do multi-passenger cosmology, because we are living in a golden era where there is equal amount of efforts coming from EM sector with a large number of missions. And with this, I will end my talk with the final slide on the summary, saying that gravitational wave sources and EM observations together brings a completely new way to explore the cosmos, not only for measuring the expansion history, but also for testing GR, measuring gravitational wave bias parameters, understanding about primordial black holes, and certainly also about formational channels of black holes and its properties with galaxies. So in this, I'll end my talk. Thank you very much for attention.
Thank you, Sivadeep. Let me invite people to open their microphones and actually clap so we can all hear. So let's do that. There you go. Okay. There are a few minutes for questions. Let me see if there are any raised hands. Okay, Sriram Kumar.
Yeah, hi, Sivadeep. Thanks for a wonderful talk. I was puzzled by the fact that you are able to link the fraction of primordial black holes and the secondary gravitational waves. There can be different sources for those gravitational waves, while primordial black holes, typically has to be generated during inflation, while there can be primary, secondary gravitational waves from different sources. So can you clarify how you get able to link them?
Totally. So when you generate if primordial black holes are generated during inflation, there are two distinct signatures. One is at the low frequency, which is basically from the second order corrections, which you see through the pulsar timing array. Another is when these itself black holes merge. And that you see in the higher frequency in the LIGO, Virgo, Kagra. And I am talking about the one which are when the primordial black hole coalesces. Okay. And not the one which you are forming from the formation, not from the fourth order in the delta phi, which gives you a power spectrum in B or secondary B modes.
I understand.
So the key point is, but let me address this, answer this in a different way, that why is this possible to distinguish? You asked a very important question, and I also emphasized that in my talk, that this is a smoking gun. What do I mean by that? When you go to high redshift, let's say you go to redshift of 5, your star formation history tells you that black stars typically form around redshift of 2, 3-ish, and it goes down. If there are primordial black holes exist, they will be existing also at high redshift, at redshift 5, redshift 10, and so on. Now the question is that now if I see coalescing binaries from up to very high redshift, I can ask how loud is this background? If you see a very loud background, that background within our understanding of star formation rate and also some future observations that are possible, we'll be able to limit what is the maximum value you can expect from astrophysical black holes. And there where you start distinguishing them. So the key feature when you start distinguishing are two things. Number one, the amplitude of the stochastic gravitational wave background. If there are primordial black holes, you expect to see louder background than the one which is from astrophysical. And that's the one which you are seeing over here, is that is for PPHs shown in dashed lines, your amplitude of a gravitational wave signal is orders of magnitude higher than if you have a gravitational wave signal from astrophysical black holes shown by dotted lines.
But this also assumes that the fraction of primordial black holes is reasonably high, number one, and they happen in a certain mass range, right?
Right. So depending upon the mass ranges. So if you go, so this plot is for black holes of the around 30 solar mass and above. If you go to subsolar black holes, the property remains the same. You have a different amplitude. And I've shown with one of my students, Matthew Minima, in one of our papers, that for subsolar black holes, this is possible from third generation gravitational detectors. So I'm only showing you results from what is possible from LVK, but in future with third generation, we'll be able to go also to subsolar black holes and measured the stochastic background. And the reason is very simple, is basically you start considering the ratio dependence of the merger rate.
I understand. Thank you, Sudeep. If I have questions, I'll write to you. Further questions, I'll write to you.
Absolutely.
Yeah, so just a very quick comment and a question. I think there could be contribution from population 3 binary black holes. We don't know what the population is, and that could contaminate everything. You know, people have, you said, oh, you know, if it is redshift 8 or 10, it has to be primordial black holes. That's not true at all. People have formulated models in which even up to redshift of 30, you could have population 3 black holes. Anyway, my question was about really the Hubble constant. If you go to that comparative slide, the famous comparison slide, there are already tens of experiments that are complementary to the early universe and the supernova one, and they have not resolved the tension, even though, you know, they are all over the place. If you wait for another 5 years, we will add another error bar here. It may occur anywhere. Why do you think it will resolve anything at all? What difference does it make to cosmologists? One more error bar here.
Right. So let me answer to both the comments. So let me at first go back to the one on primordial black holes. So it's totally true that there is going to be black holes of the POP3 type. And one can then ask, what is the contribution of black holes and stochastic gravitational background from the third generation detectors? As we exactly said, true, we expect black holes from at a shift of 30. And what people have done is they have constrained it from in combination with the reionization history and asked, what is the maximum limit you obtain on the stochastic gravitational background from these POP3 stars? These are work by Zoltan Hyman and his postdocs who have shown their background is pretty low than what you would have expected from primordial black holes. The reason behind this is that primordial black holes predicts a very simple scaling relation of with redshift, which is not the case for the third generation like POP3 stars. And as a result, the shape of the distortion is going to be pretty different when you combine POP3, primordial, and the one which is in the low redshift in the stochastic gravitational background.
Okay, let's leave it at that. Unfortunately, we are running late. We can come back to it if there is time. And if you're going to remain connected, we can come back to it, or we can correspond over email.
Okay, sure.
Because it's more a sociological.
Yeah,
my second question is more sociological than scientific. So let's thank Sudeep again for this very exciting talk and, you know, the prospect of multi-messenger astronomy.